Greetings, Internet users. At night, we can see the darkness of the sky dotted with some luminous points that we call stars. Also, from the photos taken by astronauts in space, we can see a black sky. In some cases, when the camera has enough exposure time, we can see stars in a black sky. However, this shouldn't be the case. The darkness of space is caused by the absence of light, and it is supposed that space is filled with billions of stars radiating light in all directions. Therefore, it doesn't seem understandable that space is black. The sky should be overflowing with lights from those billions of stars, including those from other galaxies. But there is an explanation for this, which proves that space is infinite in terms of its length, but finite on a temporal scale, because it had a beginning. The light produced by each star disperses uniformly over distances, but its intensity decreases as it moves away from the source. This is the reason why we see stars as small luminous dots. Their distance from us is so great that the intensity of their light reaching us is very low. Furthermore, due to the lack of an endpoint in space, the light will never reach and illuminate any background or spatial edge. The second reason is caused by the expansion of our universe. Space is not as static as it seems. It expands in all directions and in an accelerated manner. A light source in motion can change its color, known as the Doppler effect. When the source approaches the observer, its color tends towards the blue end of the visual spectrum. Conversely, if it moves away, it tends towards the red end. This doesn't mean that a red star in the sky is moving away from us. The Doppler effect must be measured with a special device called a spectroscope to determine if the star or galaxy tends towards blue or red. Considering that space is expanding, it implies that all other bodies are moving away from us, causing their light to always tend towards red. The farther they are, the redder they appear. Most galaxies and stars in the universe are so far away from us that their light decreases in frequency, meaning it falls into the infrared spectrum. Since our eyes are not capable of seeing those wavelengths, we interpret it as the absence of light, which is darkness. The visible light that we perceive is a beautiful range of colors visualized in the rainbow. However, we have never stopped to think that everything is infinite. Therefore, the spectrum doesn't begin with red and doesn't end with violet. There are more colors. If we could see X-rays and radio waves, undoubtedly, the universe would be much brighter and with colors we have never imagined. The truth is, we are blind to the wonders of the universe. For example, this is the galaxy or Milky Way in various wavelengths. X-rays reveal extremely hot gas in vibration due to its high energy and remnants of stars that exploded tens of thousands of years ago. Gamma rays allow you to see black holes as bright fading points in the distance. Infrared light allows us to see clusters of dust and gas throughout the galaxy, as well as dense clouds where stars and planets are being born. Microwave radiation provides a view of the cosmic microwave background, the echo that comes from the Big Bang at the beginning of the universe. Radio waves are the least energetic and can discover the most energetic objects in the universe, such as pulsars, quasars, and active galaxies. That's why it is much more interesting to take photographs of space in other wavelengths, as they reveal more scientific details. That's the reason why many photos of other planets in space are taken in different wavelengths with various filters, because we are here for science, not tourism. On the other hand, another evidence that the universe is expanding is that it is black. The farther an object is, the faster it expands. Many stars in the universe are so far away that their light has not had enough time to reach us. But the most important aspect of space being black is the vast distances between stars. Everything is very far away to such an extent that the stars are so distant from each other that if we were to travel in a spaceship faster than light in any direction, we would never collide with any of them, not even if we tried on purpose. We have all heard of the Andromeda Milky Way merger, and some imagine collisions between stars and planets. However, the reality is that the stars of each galaxy will never collide with each other. They will only disturb their orbits. Although space is black, during the day we see the blue sky when sunlight interacts with the Earth's atmosphere. This happens because the particles that make up the atmosphere intercept sunlight and separate it into colors, something similar to what happens with a prism. As we know, although the sun has a spectral classification of a yellow dwarf corresponding to the scientific color, in reality, it is white, and sunlight is composed of all colors. Each color travels in waves of different lengths. We can think of them as a series of waves traveling closely together or more spaced out. When entering the atmosphere, light collides with the gases and particles in the air. Depending on the size of these particles and the wavelength, different effects can occur. Sunlight is composed of colors ranging from red, orange, or yellow, which have a longer wavelength, to green, blue, and violet, which have a shorter wavelength. These latter tones, as they travel through the atmosphere, have a higher probability of encountering particles that are larger than the wavelength and are scattered across the sky. This is known known as Rayleigh scattering. The blue color of the sky is due to a phenomenon called Rayleigh scattering, which refers to the selective scattering of light by particles that are smaller than 1/10 the wavelength of light. The ozone layer in the upper regions of the atmosphere absorbs most of the ultraviolet light from the sun. The particles and molecules in the atmosphere scatter the remaining ultraviolet light of visible frequencies. The color that is most scattered is violet, followed by blue, green, yellow, orange, and red in that order. In reality, the sky on Earth is violet in color. Violet light scatters more than blue, but our eyes are not very sensitive to violet light. They are more sensitive to blue. That's why we see the sky as blue. As we ascend in the atmosphere, the number of available molecules to scatter light decreases, so the sky appears darker. In places where there are no molecules, such as on the moon, the sky appears black with a very bright sun. Sunrises and sunsets on Earth can be as reddish as this due to the scattering of long-wavelength radiation. When sunlight rays hit the surface more perpendicularly, the blue colors scatter, giving that bluish tone to the sky. During sunrise or sunset, the angle of the sun's incidence is lower, and the rays pass through more atmosphere, favoring the dispersion of reddish colors. That's why some sunrises or sunsets have that color. On other planets with an atmosphere, the sky is very different. It is not always blue. There is a trick to guess the sky of planets without landing on the surface, and it consists of observing the sequence of the atmospheric air that curves around the planet. This method works in most cases, although there are some exceptions, as we will see below. For example, on Venus, which has the densest atmosphere among the rocky planets in the solar system, from its surface, the sky would not be visible, and we would only see the illuminated clouds. Considering that Venus has a high albedo, reflecting almost all the incoming light, the clouds would appear white with a slight tendency towards yellow. Therefore, we owe this yellowish color to the sky. Mars has a very tenuous atmosphere, but it is still capable of scattering light. Although the majority of its atmosphere is composed of carbon dioxide, it is the suspended particles of iron oxides that give the Martian skies a light ochre color with a hint of yellow during the Martian day. However, depending on the amount of particles present, the color can vary significantly. At sunset, the red planet takes on blue and violet tones. Although there haven't been actual images taken of Jupiter's atmosphere, artistic representations often assume that the planet's sky is blue, albeit darker than Earth's, due to the solar light being, on average, 27 times weaker at the upper limits of the atmosphere. The sky at the top of Saturn's atmosphere is blue, according to images from the Cassini mission at the time of its demise in September 2017. However, the predominant color of its cloud cover suggests it may be more yellowish further down. On Titan, Saturn's largest moon, if we were on the surface, we would see the sky in a mandarin color. Interestingly, as we elevate above its surface, the sky would gradually turn bluer. Let's move to Uranus. Judging by the color of its atmosphere, the sky of Uranus is probably a light blue, or cyan. Neptune could have a somewhat familiar sky, but with a deeper blue color, judging by the color of the atmosphere surrounding the planet. Pluto's atmosphere consists of a thin layer of nitrogen, methane, and carbon monoxide gases, too thin for the sky to have a significant color. Based on photographs, we might encounter a black sky with a slight blue haze at sunset. On other planets, the skies could be very different depending on factors such as the type of star, atmospheric composition, amount of light, and the incidence of sunlight on the planet. For example, in systems with red dwarf stars, both the planets and the skies tend to have reddish or brownish hues. As we venture far from Earth, we can imagine beautiful skies with exotic colors bathed in 1, 2, or more suns. The beauty that can exist on other planets surpasses anything we can imagine. If you liked this video, give it a like and don't forget to subscribe. Share it on social media and leave your comments.